Hey guys, this is 6.5, and what we're going over for 6.5 is the properties of logarithms. The reason we're doing this is because logarithms, as we learned last class, are the inverse of exponential functions. Sorry, logarithmic functions are the inverse of exponential functions. And so we're going to practice 5 different rules for how to use logarithms that are a lot like the rules for using exponents. And then because we have learned how to apply these rules, we will then be able to do very complex things in 6.6, which is our final lecture together. So let's get started. Okay, so let's just begin by going over the properties of logarithms. We know that logarithmic functions are the inverse of exponential functions. We know how to convert between exponential form and logarithmic form. So today we are going to condense and expand expressions with logarithms. So I'm going to separate the first two. From the last 3. And then I'm going to label these. I'm going to label this side. These 3 examples are the condensed version. It's feel like the condensed logarithmic form. And then these 3 would be the expanded logarithmic form, but they're equal, the same thing. If these were numbers and you put this into your calculator, it would give you the same output as if you put this into your calculator. These are seen less often, so we're mostly going to be using the condensed and expanded, the last 3 today. Okay, so number 1 says if you have a base of a and it is being raised to the power of an exponent that is a log, and your log has the same base a as the base of the exponent, base a and the logarithm base a undo each other, and you are left with whatever it is the log of. You are left with m, right? So for example, if I had 9 to the power of log base 9 of 8, the 9 and the log 9 would cancel out, and I would just be left with 8. Good. The next one is, it's kind of the same thing. So we have log base a of the base a raised to a power leaves you with only that power. The other 2 things, the log of a and a, cancel each other out. So we could say, for example, log base 6 of 6 to the 7th power leaves me with 7. Simplifies to 7. Okay. And where's my calculator? I could show these examples. So we have 9 to the power of log base 9 of 8, log to the power of, sorry, 9. So you can't do log. 9 to the power of log base 9 of 8, or of anything, will give you that number. And then we have, starting with log, just because it's easier to see, I'm going to use only log base. So log base 6 of 6 to the power of 7 gives me 7. And if I were to change those numbers, obviously it would still, the rule would stay the same. Okay, so down here is where we learn to expand and condense logarithmic expressions. If you look at the left-hand side, they are each a single log. And this is the condensed form. The right-hand side is the expanded form. and the properties show us how to go between the two. And like I said, it's just a little bit like the rules for exponents, right? When we master this, we will be able to solve more complicated logarithmic and exponential functions. So number 3 said, when you have a log of things being multiplied, if you have a product, right, you can expand it by taking the log of each individual part being multiplied and then adding those together. Oh, sorry. And it doesn't matter if you have 2, you can have 3, you can multiply as many different ones together as you want. You can make that as long as you would like, okay? Number 4 says if you have the log of a fraction or of a division problem, right, which is also called a product, you can expand that by taking the log of the numerator and then subtracting the log of the denominator. Number 5 says that if you have the log of something and it is being raised to a power, we can bring the little exponent r down and multiply it by the entire log function and you'll get the same answer, okay? It becomes a constant with the log. All right, so those are the properties of logarithms. And we're going to use them to simplify. We're not really solving much today. We're just going to simplify. Okay, and here they are. I'm just going to have this nearby in case I need to reference it. So for example 1, here, the first example in example 1 is 3 raised to the log base 3 of pi. A base being raised to an exponent that happens to have the log of the same base means that a and log a cancel each other out and we're left with m. So 3 and log 3 cancel each other out and we are left with simply pi. We simplified to pi. This one we can check because those are all actually numbers I can put in my calculator. So 3 to the power of log base 3 of pi is, gives me the same decimal in my calculator as just putting in pi. So now this one says 7 to the power of log base 7 of the square root of 3. It looks just like that other one. So we can say 7 cancels the log of 7, or sorry, the log base 7 to leave us with the square root of 3. This third example, ln, remember, means the natural log. So ln of anything is also the log base e of anything. So we're really saying log base e of e to the negative 13, right? That's just like number 2, log base a of a raised to r. Log base e of e raised to negative 13 will give me negative 13. But let's put that in our calculator. So I could either say, oops, let's try to push the down button and miss it. Log base e of e to the negative 13 is negative 13, or just natural log of e to the negative 13. Gives me negative 13. So we showed that the natural log and the letter e, the number e, cancel each other out, and we're left with the exponent. All right, and we and remember, so this is true because the log, taking the log of a number when that same number is the base, will always equal 1. All right, so let's look at an example, okay? So I'll say log base 10 of the number, log base 10 of the number 10. Okay, and I'm going to say equals log base 10 of the number 10 equals 1, right? Taking the log of a number when that same number is the base will always equal 1, because remember, we start with the base. So I'm going to translate this to exponents that will look more familiar to you. So we take that first 10, and that becomes our base. And then that number 1 goes right here. Oh, sorry. Going in a circle. So going in a circle, 10 power of 1 equals 10. If I was to go backwards, the log base 10 of 10 equals 1. 10 to the first power equals 10. So that's why that works. All right. And that third one, which they are calling, or sorry, that fourth one, which they are calling example 2, they're asking us to expand this. And so we need to use 3, 4, and 5 to expand. And let's look at this. We have log base a of x squared times the quantity x plus 1. Sorry, the square root of x plus 1. There's no multiplication symbol here, but this is a grouping symbol, just like parentheses. So it's like putting an x squared in the parentheses next to the parentheses of the square root of x plus 1. That's how I know it's multiplied. Okay. So I'm looking at a single log of things being multiplied together. A log of things being multiplied is number 3. So I can separate them by taking the log of each and writing it as a sum, right? Log base a m of n equals log base a of m plus log base a of n. So I would have, if I were to do that right here, I would have log base a of x squared plus log base a of the square root of x plus 1. Good. So if I have something log base a raised to a power, I can also bring it down. So I can change this. There's one more change I can make. I can take this 2 and I can move it down, right? Just like that r gets moved down in front of the log a of n. So now this looks like 2 log base a of x. Good. I don't have a rule that uses the square root, but I do remember that let's go over here. The square root of x can also be written as x to the 1/2. Do you remember that? I think it's from unit R back at the beginning, our review. So basically the 2 is from here and the 1 is from here. So anything you have under a radical, you can change into a fraction of an exponent because those are the inverse of one another. So if this was the cubed root of x to the first power, that would be x to the 1/3. If this was the 5th root of x to the 3rd, for example, then you would have x to the 3/5. Good. So I'm going to rewrite this as log base a of x plus 1 to the 1/2 power. And then I can rewrite that as 2 log a of x plus, and then I'm going to bring that 1/2 down as my last step in the simplification. 1/2 log base a of x plus 1. Yeah. So my final step is I bring both the 2 and the 1/2 down in front of each log expression. I was able to start with a single log and expand it to 2 logs because a and x are variables instead of numbers. This is as simple as I can make it. I'm not solving anything. I'm just changing it from, we would call this the condensed form to the expanded form. Just making sure we know how to follow all the rules to change between those two forms. All right, example 3, and here's our information. All right, so for example 3, I have the natural log, which is just log base e, right, of a fraction. We have a rule for a log-based fraction. A log-based fraction, log a of m over n, can be rewritten as a subtraction or a difference, log a of m minus log a of n, right? Log of the numerator minus the log of the denominator. So I'm going to do that first. Natural log of x squared over x minus 2 to the 4th becomes the natural log of x squared minus the natural log of x minus 2 to the 4th. Good. Okay. And because I have a log to a power in each example, I can use that last property, property number 5, to bring that power down in front and multiply it by the log expression. So here I'm going to bring the 2, use a different color, here to accentuate what I'm doing. Here I'm bringing the 2 down, here I'm bringing the 4 down. So now I have 2 natural log of x minus 4 times the natural log of x minus 2. And the parentheses, you can include the parentheses or not. I needed the parentheses, or I need the 4 outside the parentheses here because it's being because it's being distributed to both the x and the -2. Here, it's only going to the x, so you could put the 2 outside or inside. I liked it inside because it shows that I'm putting that in and taking the natural log of it, but they mean the same thing. So I could have put parentheses here too, right? If I wanted, just to show what we are taking the log of. All right, that is as simple as I can make it. And you can write it as 2 natural log of x minus 4 natural log of x minus 2 without the parentheses. You would be okay. So we have expanded from the condensed form. Example 4, we're going to write this single logarithm as a sum and difference of logarithms, and then express all the exponents as factors. So don't leave any exponents up on top. Okay, so first, log b of the cubed root of x squared plus 2 over x squared times x plus 2 quantity squared. The first thing I want to remember is that the cubed root of x to the first, so the whole thing is x to the first, can become x to the 1/3, right? Okay, so I'm going to rewrite it like that. So I'm going to say it's log base b of x squared plus 2 to the 1/3 power divided by x squared times x plus 2 squared. Okay. So now I have the log of a fraction. I can change it to a subtraction problem. Okay. So I'll rewrite this as log base b of x squared plus 2 to the 1/3 minus log base b of x squared times x plus 2 squared. Good. Okay. And I see here I'm multiplying x squared times x plus 2 squared. That means if I look, it disappeared. All right, if I look at this, there's also so we used the subtraction problem, but the log of x squared times x plus 2 squared, I can also change into an addition problem, okay? So I'm gonna rewrite that as an addition. So we have one subtraction and we'll have one addition. So we have log base b of x squared plus 2 to the 1/3 power minus, and then I'm going to put brackets here because I need to distribute that minus sign through both log b of x squared and log b of x plus 2 squared. Okay. Or if you want, you can skip this step and just put a minus here and a minus here. That would be the same as distributing the minus sign. So that would be log base b of x squared plus 2 to the 1/3 minus log base b of x squared minus log base b of x plus 2 squared. Distributing that negative sign. All right. Finally, I move the exponents down in front because it said express all exponents as factors, right? So that means I'm going to take the 1/3, put it over here. I'm going to take the 2, put it out front here. And I'm going to take this 2 and put it out front here. So my final answer is 1/3 log base b of x squared plus 2 minus 2 log b of x minus 2 log b of x plus 2. And that is all I can do. I started with a log of a polynomial fraction and expanded it to the difference of 3 unique logs. And finally, we will use these reading it as I was speaking. We will use these properties to now go in the other direction. So before we were going from condensed to expanded. Now we're going to go from expanded to condensed and make it as condensed as possible. If you'll notice, we're still not solving it because we still have a variable here and a variable here. We could solve this one, but it just says write as a single log. It does not say solve. Okay. So now we have log base b of 5 plus 3 log b of 2. Remember, our last step was always moving that exponent out front, right? Moving that exponent out front was always our last step. We moved the exponents out front here, 1/3, 2, and 2. So when we're going the other direction, the first thing we do is we move the exponent back to its place. So now I have, this becomes log base b of 5 plus log base b of 2 to the 3rd power. Good. If I can add these two together, hey, there it was. All right, if I'm adding these two together and I want to condense it, that means I'm going to multiply them and put them both under 1 as the log of 1. So log base b of 5 times 2 to the 3rd. Good. And then I just do my math. 2 to the third is 8. 5 times 8 is 40. So my final answer is log base b of 40. Yeah. All right. Again, the first thing we do is move this back into the exponent. Oops, went too far. Move this back into the exponent position. So now I have the natural log of 27 to the 2/3 power minus the natural log of 6 squared minus 9. Good. If it's a subtraction, I can condense it to a division problem or a fraction. So now I have the natural log of hard to see. I'll just start a different color. 27 to the 2/3 power over 6 squared minus 9. Good. So if I were to put that in my calculator, 27 to the 2/3, you can put it all in your calculator if you want. Don't put the natural log, just put this. But 27 to the power of 2/3 is 9. Good. And then 6 squared minus 9 is 27. So that becomes the natural log of 9 over 27. And I can divide both of those by 9, right? That becomes 1 and that becomes 3. So it's the natural log of 1/3. And if we were to put all of that into our calculator, so we said 2/3, oops, 2/3 times the natural log of 27 minus the natural log of 6 squared minus 9. Oh, we can't do a fraction there. And that is the same as the natural log of 1 divided by 3, that you get the same decimal. Good. All right. Now log base b of x squared plus 4 plus log base b of 4 plus log base b of x minus log base b of 7. So that looks like a bunch of these. They're all addition. They all have the same base, so I can multiply them all together. So I'm going to rewrite it as a long multiplication. So now I have log base b of x squared plus 4 times 4 times x. See where I got each of those? Minus log base b of 7. Good. Now I'm going to multiply all of these together. The easiest way I think to do it is to multiply the 4 times the x. I get 4x. And then I'm going to distribute that 4x through. So I'll just do that real quickly. Log base b of 4x times x squared plus 4. So I combine these two, put them in front, minus log base b of 7. Now I'm going to distribute that 4x. 4x times x squared becomes 4x to the third. 4x times a positive 4 becomes 16. And that's still log base b of 7. Good. And then, because that is a subtraction problem, I can condense it to a fraction. There's nothing I can do to simplify this except turn it into a fraction. So my final answer is log base b of 4x to the third plus 16 over 7. I can't divide 4x to the third by 7 and get a whole number. I can't divide 16 by 7 and get a whole number. So I can't simplify it any further. That is it. And so remember, we did all this just to make sure we have the skills to solve complex logarithmic and exponential functions in our final lesson. Thank you guys so much. I hope that you have a good rest of your day, and I'll see you in 6.6.